Greetings, dear students. So this is the second part of the second lecture. So I'm going to continue, and I welcome you guys to it. And I guess by now, at this point in time, you should have done your first lab because it's going to be due and done already. So I guess you have done the first lab, and you're looking forward to the second lab, and that will come on the 17th of this month. So do well to check, and the labs are on the Uzem platform. It's there. Scroll down and look at all the contents on the page. So if you are doing the labs, go for it. If your course doesn't involve the labs, just look out for the homeworks and the quizzes that will be coming this week. Please don't miss out on anything. And those of you that have been asking questions about the lectures, the videos you're watching are the lectures already. Those of us on the face-to-face, watch the videos, come to class. We will go over the lectures again. For those of us on the online, this is the best way we can do it, and you get the lectures. So that's the information I'll give, because a lot of people have been sending emails asking questions. So I guess this answers your question. So let's go right into it. So for the second part, we're going to continue from atomic masses, and we will go right into the others. So atomic masses of an element indicates how heavy on average an atom of an element is when compared to another. So notice that the atomic masses are based on comparison. We know what atomic numbers are. We've explained that, and it's denoted Z, and we know what mass numbers are. That one is denoted A. So now we're looking at the atomic mass. You're trying to compare the mass of one element to another, because remember, I said in class, no two students have the same student number. No two students have the same student number. So every element will have a different mass from the other. So if we know one, we can compare with the other, because you can compare different student numbers. And most of us in the university have our student numbers according to the years we registered or entered into university, and then the last 4 digits are based off your unique. What makes it unique is just year, and then the 4 digits that are attached to the year. So that's how the system goes. So in masses, you compare one with the other. So we have carbon 12 scale, which is based on the most common isotope of carbon. And the carbon 12 there is the 12 there is the atomic mass unit. 12 there is the atomic mass unit. Notice that you have a C there, and on top of the C you have the 12. And we say this is where the A is, and the Z, which is your atomic numbers below. So we say that an atom, half as heavy as a C12 weighs 6 atomic mass units. So we see that an element half as heavy as it will weigh half of it. So it's the comparison that we're doing with this. So remember, we talked about what isotopes are, and now we're looking at isotopic abundance. Isotopic abundance. We say that isotopes are, it's a situation where you have 2 elements having the same atomic number but different mass number, having the same number of protons but different number of neutrons. That is still what it implies, because your mass number is literally your number of protons and the number of neutrons. So that's why we say there are 2, and I explained it. I said with human beings, 2 people that look alike but are yet different because they have different names are twins. They look very much identical but are different names. So that's kind of like the situation that happens with atoms. So, and we have abundance. Abundance means that there's a lot. So atomic masses can be determined using a mass spectrometer. Mass spectrum, anything that has meter attached to it, is literally measuring something. You have a speedometer, measures speed; thermometer measures temperature or heat. So the mass spectrometer is measuring mass the spectrum. That means you can have different masses. So a gaseous atom is ionized at low pressure by removing electrons. Notice that most of the times you always see low pressure. Is the ionization of gases at low pressure. Ionization of gases at low pressure. Many times, the time you look at cathode ray tube apparatus at low pressure, we're looking at this too at low pressure. We'll see that the bulbs and all the lighting system is literally gas stored up in that tube at low pressure to give off light. So we'll see the device, the workings of the device in the next slide. So I'll just quickly explain this and make it clearer in the next, because the image says a lot about it. So the cation is a positively charged ion. The anion is negatively charged. How you always remember that the cation is positively charged is from the pets that we know as cats. People get a positive feeling from cats, so just remember it as cations positive, and then anions because you have an an to ions, which negates it. Because if you have normal, to say something is negative, to say normal in the negative sense is abnormal. So the cations that form are accelerated towards the magnetic field using a potential. So I think I'll just go and explain the image so that it will make more sense. So look at what happens here. So what you have here is a gas inlet, and the gas goes through this hole. It comes in here and goes through this hole, and these two plates are called the acceleration plate. So you have the electron gun beneath here. So what the electron gun does is that the electron gun knocks out the electron, so that what passes through the slit is the cation. So and the cation goes and collides with this magnet. Notice that you have two distinct ions, and these two distinct ions, one is heavy, one is light, and on collision the lighter one will be deflected, the heavier one will get past the collector and hit the detector. So how this happens is that the lighter one, we know its mass, and then we calculate the speed at which, not the speed, the weight, which invariably tells you the speed at which this one gets through and hits the detector, and then there's a mass that is done and the voltage on the basis of the voltage and all of those things. You can calculate the relative mass between two, because if two runners are running, the speed of one runner is known. You can be able to determine the speed of the other runner on the basis of how fast or how slow one gets there before the other. So that's the principle by which the mass spectrometer works. So after the whole thing, you discover that the mass of fluorine, which is what was compared with carbon, is 1.583 times heavier than that of carbon, and on the basis of that you just multiply 1.583 to 12 and you get the atomic mass unit for fluorine. So this is how the device works. It does all of these things and gives you values. So that's how it happens. The determination of to now determine the mass of elements that naturally occur as a mixture of two isotopes, you now require to know the mass of each isotope and the atom percent of the isotopes, which is your percentage abundance. Note that the first one we did was based off comparing the one that is known to the other of different elements or different atoms. Now you're doing for the same element that has two different isotopes. Same element, two different isotopes. So what you do now, you compare the mass with the isotopic abundance, and we'll have a graph to show how this is done with chlorine. Notice that the first example was with fluorine, the one we saw with the mass spectrometer device. This one now is with chlorine, and the mass spectrometer can determine the isotopic mass as well as the isotopic abundance. Remember what we said previously, how you can do it is to determine the mass of the element as well as the isotopic abundance, the mass of the isotopes as well as the isotopic abundance. So in the image you have, in the graph you have, notice that there's a plot of the percentage abundance against the mass, and chlorine has two isotopes. One of them is 35 or about 35, and the other one is 37. And notice that the isotopic abundance is around 70 something, and the second, that's for 37, is around 20 something. Very important. Going forward, notice that it's not the bigger the mass, the bigger the abundance. The percentage abundance is entirely independent of their weight. So don't always assume that if you have 35 and 37, 37 will always be bigger in abundance than 35, because that's not how it works. Because the abundance of elements are not tied to their masses. They are entirely different from their masses. So don't make that mistake, because we're going to do an exercise that that's probably going to throw you off balance if you have that at the back of your mind, that probably the masses are related to the abundance. So now to calculate it, you have to do, remember, I've said this on several occasions, percentage simply means over 100. Per means over, cent means 100. So it means percent is over 100. So for you to take out that sign of percent is to divide this entire value by 100 and multiply it to this value here to get the percentage in particular for that part, and then you do the same for this, and then notice that once you add this and this, it totals up to 100. So it means that if you get the values for these two and add them together, you really will have the relative abundance of the two isotopes. So, and that is the goal. That's what we're trying to do. We're trying to find the relative abundance, which is the 100% of the chlorine as well, looking at chlorine. So now notice that you're doing the atomic mass of Y, which is this atomic mass unit, the percentage over 100, so that the percent would cancel the percent, the 100 will cancel the percentage, the isotopic abundance, and then you now add it to the second, what I was saying here, what I just explained here now. So to do that directly to get an answer, you will literally do this true, multiply true, and add it to this other part, and what you have is the relative mass of chlorine, which is 35.46 or 25.5. So I trust that is clear. Then let's do our example. Our example is slightly different, or the reverse of this. So, and notice that all of them are related. We talked about fluorine at the beginning, chlorine secondly, and bromine. Notice all of them end with a unique INE. Fluorine, chlorine, bromine, and they're all part of a group, of which some of you have gotten it right already. That's if you thought about it. If you didn't, or you don't know, they are all called the halogens. They're in group 7 of the periodic table. We'll see them ahead when we're looking at the periodic table shortly. We'll do that very soon, and we'll definitely do that in this part of the video. So bromine is a red-orange liquid with an average atomic mass of 79.90 atomic mass unit. Guess what's that value? That's the relative abundance or the average of the two. So just put that at the back of your mind, that to effectively solve the questions, you have to understand the question. So its name is derived from the Greek name bromos, which means stench. It has two naturally occurring isotopes, Br79, which is 78.92 atomic mass units, and Br81, which is 80.92 atomic mass units. So notice that 79, the atomic mass unit you have in front of it rounds up to 79. 81, the atomic mass unit you have there rounds up to 81. So those are the two different isotopes, and those things are not in percentage. They're the masses, and then you have the relative mass. So the question is, what is the abundance of the heavier isotope? So now you know that we're looking for the isotopic abundance. The atomic abundance is not given in any way. So if you read the question and you saw isotopic abundance somewhere, it's obvious that you're wrong. So we're asked to find the isotopic abundance, or the percentage abundance. So now remember from the formula we were given previously, this is what it looks like, and it's equal to the relative or the average. So what you're going to do is to reverse it, and the goal is to find this and this. Notice that you have two unknowns, which is y1 and y2. And the clue I'll give you before I get you to solve it is that since you have two unknowns, you should come up with something that enables you to find the two unknown as one. And my question to you is, what is the relationship between this percent and this percent? What is the relationship? Notice that the relationship between the two is that if you add both of them, you get 100. If you add both of them, you will get 100. And in this question, you are asked to find the abundance of the heavier isotope. Which one is the heavier isotope between 79 and 81? You guessed right, it's 81. Obviously, it's 81. So I want to now find the percentage abundance of 81. So let's make the percentage abundance of 81 x, and the one for 79, let's make it 100 minus x, because if the one of 79 was y, to find y, it's going to be 100 minus x, of which, if it was x and y, which is 81, which is x, and 79, which is y, it's going to be x plus y equal to 100. So when you move y or move x to the other side, it's going to be y is equals to 100 minus x. So I've given you a clue already that if you are good with maths, you should already start solving. So just take your time and solve it quickly. So pause the video and solve this, and then we'll move on from there. And my encouragement is try to solve it. If you do it yourself, you're training yourself on how to do these things. Nobody's born with the ability to solve problems or solve math. We had to practice to learn. So this is your practice. Take your time and practice. If you don't practice now, the homework and the quizzes will force you to literally practice, and it might be late. That will not be a good time to practice, because you need to do well in your homeworks, in your quizzes. So thank you for pausing the video and doing it. So let's just go right into it. So this is outlining what you know already that we do have. This is the formula repeated to us. So just explain what I explained earlier, that all the abundance must round up to 100. So what I said was 100 minus x is equal to y. So we use x for the behavior so that we can, when we get the value for x, we know that that's the behavior. So when we put everything in their place, this is the relative abundance, this is the one for the second, you multiply it through by this, and this is the one for the one that's required. Once you do this, this will cancel this and multiply into this, and then you have this here which you multiply through. You multiply through, and then you have this value minus this and this. Sorry if you are hearing rumblings at the time of the recording. It's raining outside and thundering, so don't be scared. It's a natural phenomenon. So when you multiply through, when you open the bracket, this would divide through to this and multiply by x, and then you have this value. So notice that you have 78.92 and minus 0.7892x. So notice that this can go over to the other side, and when this goes up to the other side, when you multiply 79.90 from 78.92, you have 0.98. And once you multiply when you subtract minus when you subtract 0.7892 from 0.8092, you have 0.02. And when you divide both sides by 0.02, you have 49, which is because you're dividing 0.98 by 0.02, so you have 49, which is your answer that you can see here. So if you have a problem with change of subject formula, if you have a problem with mathematics in general, you literally not understand what just happened here. But if you slowly walk it through and try to do it yourself, you get it very quickly. So it's not some complicated of a math. So at the end, we know that our atomic mass for bromine is 79.90, and it's just halfway to both of them, which is like kind of your average, and it's quite reasonable because it's nearly equal to the two isotopes, similar to what we did with chlorine, where you have 35 and 37, and the middle ground is 35.5, which is your average. So now we go to masses of atom in grams. Masses of atom in grams. And remember, we have always been talking about the masses of atom in atomic mass unit. So we want to take it to measurement that is relatable, because you've never seen a device that measures things in atomic mass units. They always measure things in grams, kilograms when you take it higher, and you drop it a little bit, milligrams, and it goes on and on. So it's necessary to know that mass of an atom in grams is necessary to know that, and the quantity of matter can be determined by weighing. So how you get masses or know a mass of something is by weighing it. So we said 1 He, which is helium atom, is 4 times as heavy as the H atom, which is hydrogen atom. So the reason for that is because helium has a mass of 4.003 grams and hydrogen has a mass of 1.008 grams, and that's how comparison is being made, because actually if you put a scale of hydrogen against a scale of helium, you need to put 4 hydrogens to balance the scale. That's literally what it means. So the Avogadro's number that we're going to look at as our conversion factor to move atomic mass units to grams is what we're looking at now. Avogadro's number is actually a number derived by an individual called Avogadro's. And the number of atoms of an element in a sample whose mass in grams is numerically equal to the atomic mass of an element, and the number is literally 6.022 times 10 to the power of 23. That's a lot of zeros. That's a lot of zeros. And I often joke with the students. I said, if you have your account running these kinds of zeros, will you still be in the university studying, or you just quit school and just quit school and never to return again? So it's quite a lot, and we'll see why it's that way when we look at the Avogadro's number in a calculation, or in principle, or in action. So we have an example, and we're considering arsenic gas. Arsenic, and arsenic is they used a lot in movies as crime stories, as poison. So they put it a little bit. If you watch movies, they put it as poison in drinks, tea, whatever drink. You just drop a little bit of it, and when you drink, the person instantly goes out, because a little amount is enough to cause damage, like havoc in the system. So the Avogadro's number is given as the usual 6.022 times 10 to the power of 23, and we're asked to determine the mass of an arsenic atom. So let's do this one, because some people it will be difficult for them to walk it through. So notice that the conversion is such that you're moving from atoms to grams. You're doing the conversion from atomic mass units to grams, and the conversion factor is the Avogadro's number. So how it will happen is that we said previously that if you are converting to grams, you have to put the order. The wanted should be above, the initial should be below, and then you multiply through by the value given, which was say one atom of arsenic. So once you do that, this will cancel this, and then this will divide itself, and then what you're going to end up having is 1.244 times 10 to the power of minus 22. Notice that there's a reason that is minus 22. Notice that the big value now has turned negative. And remember, an atom is not a grain of rice. An atom is a lot of times smaller than the grain of rice. In fact, it's smaller than a particle of dust. So it's a lot smaller. You're talking about a single atom. So the weight of a single atom is of arsenic is 1.244 times 10 to the power of negative 22, which is very, very small. Very, very small. You can't actually weigh that with any scale that we know of, except special scales. So because the atoms are so tiny, their mass are expected to be very small. So this sounds very reasonable. So now we quickly go into our periodic table. So we're introducing ourselves to the periodic table, and there's a big reason why it's called the periodic table, and it's not by accident. It's called, even though some people call it the Mendeleev's table. Some people call it the Mendeleev's table. It was originally called the Mendeleev's table. I think then generally was accepted that it be called the periodic table. So chemical properties of elements depend upon their atomic numbers, which we can read from the periodic table. So remember, I said the atomic number is, two elements have the same atomic number, so the atomic number is in sequence. So if you have 1, you have 2, 3, so it goes in that order. So that's the sequence. Even with your student number, the first year the school started, you have people with student numbers from that year extra 4 digits, and it keeps going on and on. The new students that are in this, that's taking this course, will probably be having a student number 2020 as at the time of this video, or you watching this video. So it goes on like that. So we need to arrange them in a certain fashion, and notice that the word periodic is from the word period. And most of the times we students are familiar. We say our lectures are held in maybe this period. You have the first period, the second period, the third period. Anything table, if you have a table, you have periods, you have rows and columns. So and that is how you, and notice that most of the time the rows are where your periods are, the columns are the groups, are probably where the date and the times are. So that's basically what it is. That's literally what it is. So the horizontal rows are your periods, and then the vertical columns, are your groups, and we'll see that in more details. Notice that the periodic table have groups. So the groups in the periodic table are what we're going to look at. The main group of elements are your 1, 2, and notice that this will vary from periodic table to periodic table. This is a general acceptable standard, but some periodic tables you will just see 1 to 8, and they put probably a gap between 2 and 3 where the transition element comes. Give it some numbering system. Sometimes they can give it a different numbering system in that gap. So don't be confused when you see 1 to 18 or 1 to 8 and then 8 is neon. So 8 is helium. So 18 is neon, sorry. So notice that you have the main group, which is your 1, 2, then 13. Because after the 10, 13 will start, and then you go down to 18. And then you have your transition metals, which are your 3 to 12, which are literally 10. So if you count 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's literally 10. And then you have your post-transition metals. The word post means after transition. Pre is before transition, post is after transition. So it means that immediately after the transition metal, you have your 13, 14, 15. So those are your post-transition metals. And then you have your alkaline metals first, which are your group 1, and the whole people in group 1. And then you have your alkaline earth metals, which are your whole couple of elements in group 2. And then you have the special group of halogens. Those are the ones I introduced you to, or we were introduced to, in the mass spectrometer section of this lecture, where we looked at fluorine, we looked at chlorine afterwards, and our example bromine, and you have iodine, and you have several of them going down. And then you have the noble gases. The noble gases, they are quite noble, they are inert, they don't react, they are very useful. We'll see them in more details as we go. I think we haven't. So, and you even know them and you don't even know. In fact, they're currently in your house, or they're currently in your room, and you probably had not realized that the inert gases are there. Notice that they're called the inert gases. So this is what the periodic table looks like, and what I was talking earlier was the periods like this, and then the groups are like this. So this whole well here, this 3 to 12 contains your transition elements, and then this is the post-transition metals, and then you have your halogens, and then you have your noble gases or inert gases. So notice that the color coding is so that you have your metals, you have your metalloids between metals, and then you have your non-metals, which are on the side. Notice that there's one strange fellow. He's here and here as well. So you can guess the reason why he's in both places. used to funnily say he's a double agent. He works for the Russians and also works for the British. So he's worked for KGB and works for the British intelligence as well. So the reason for it is because he has one electron, meaning that he can be a metal and give the electron away, and he can also be a non-metal and receive as well, because he just has one. So it can depends on the reaction he's involved in. He can either quickly receive or easily give. So that's why he's in two places. When you have helium after himself. So elements in the periodic table have their arrangement. We talked about how the order they arranged is increasing atomic number. So it's easier for you to start from 1, 2, 3, and then it goes on and on. And we said at the beginning of the first lecture, around the beginning in the first lecture, that we have like 118, but I mentioned that the number has increased prior to the time of this compilation of this slide presentation. So the horizontal rows are you have the length, and then the vertical rows, you have all of those things. And Dmitry Mendeleev actually began the development of this periodic table, and I promised I was going to tell the story of the background of Dmitry Mendeleev. Okay, I'll just do it here so that you really will understand who this individual was. So Dmitry Mendeleev was, I think he's from all this Russian, the whole Russian sphere, I think one of those USSR, the Soviet Union provinces that is not far from here. He was born to a family of I think 11. So the father had a glass company, and I think at some point in time the father lost his vision, became blind, and he died. So when he died, the mother took over the family business, because there are a lot of them. He said there were 11 of them, like a whole football team, 11 of them. So the mother had to cater for them, and then something happened. Fire gutted the glass company, and things were hard for them. So what the mother decided to do was that, and Dmitry was a very bright child, so she decided to take him to the university his father had finished from. Not the university his father finished from. First, she took him to a university. The university turned him down. Then she decided to take him to the university that his father had finished from, and then he was accepted there in the university. Like some of you were accepted into Harris University at the point of this video. You accepted into the university to study. So he studied in the university, finished from the university, and got a job in the university. And he was very much fascinated about elements and the discovery of elements. So he was very much inspired and worked like no other scientist concerning having to group and place individual elements in their right position. So he was finding these elements and then was trying to work out the relationships between the elements, so that he will arrange them, and like he created a table, and then as people or other scientists were finding the elements, they were fixing into the periodic table to make the periodic table we do have now. So he helps in building it and grouping it to a great extent. That's why I told you that the table is actually named the Mendeleev table in some spheres, but generally it's called the periodic table. But actually it was named periodic table because Mendeleev was so into the periodic table that if you brought an element and placed it in the wrong, he would actually argue, because he knew the properties of each group, and he perfectly would place them in the right group. So if you had an element, he would literally be the one to come up with where it falls in the group, because he has studied it so well. So that's the story behind Dmitry, and it's quite an interesting one, because this is not only the thing he did in the field of chemistry, there are other things we'll see about him going forward. So he's quite a person to do a little bit of research on, and it will interest you the things you find about him. So So, and actually, as I said, he created a table, and till today people are still filling the table with other elements even in his death. So he left a big mark in the whole area of elements, and because basic chemistry is about matter, and matters elements are what make up the whole matter. So he really did a lot. So we're now looking at the different parts that were divided the periodic table. I saw the periodic table because we grouped it not only into group 1, group 2. We also saw that on the periodic table that you have metals on the side, and then you have the metalloids, and then you have the non-metal with the color coding that we saw on the periodic table. So the metals are elements present to the left of the diagonal line of the periodic table. That's where they are located. And non-metals are above to the right of the stairway. That's the little stairs we saw previously. And then the metalloids at the dividing line between those metals and non-metals. So they're like the ones that's a mix of both metals and non-metals. So that's your metalloids. So here we have 3 different, of which you're familiar with this fellow over here. That's the antimony we did when we're talking about nucleus symbol. This was actually the antimony we were talking about that has a symbol SB. I would have asked that question, but I've given the answer already. And then there's this sulfur, and then silver. Notice how they all look very different. 3 different elements, very different in appearance, even though this one to look like this, but very different. Their uses are entirely different. So biological view of the periodic table is that you have good guys and you have bad guys, like every good movie would do. You have the protagonist and you have the antagonist, and the good guys are obviously good, the bad guys are obviously bad. So bad in the sense that they cause harm, good guys are good in the sense that we need them, even though if you take too much of the good guys, it can go bad for you as well. So the major elements are yellow and trace elements are green. So you have carbon, hydrogen, oxygen, sulfur, and others. Those are the ones that we do need, and they're natural occurring. And then you have the toxic, and they are the latter ones, so they have their color coding, so they're pink. So some elements are essential but become toxic at higher concentration. So you have some other ones that are very, very essential, but they need to be in very little amounts. So also have, I think this is where we're going to be ending this part. We have neon, and neon obviously is a inert or the noble gas, and I know some of us don't know that the inert gases are mostly what we use to generate light, our light bulbs and the rest. Notice that those gases are what they use to fill the tubes. They use the gases to fill the tubes, and every gas has its unique color it gives off. Remember, from the cathode ray to the other, I think it was another one we were talking about, gases at low pressure. So they pass your coils through them, and then there's electricity that's passed through, and then because of the gases and then the low pressure, lights are given off. And it's very interesting. I think helium too is another inert gas that gives off, I think it's orange color it gives off in the same, and then neon gives off the reddish color, and then you have, I think, different interesting colors. I can't remember all of them. I think krypton, argon, I think it's green. It's a greenish or something. And one of them, light blue. They have different colors that they give up on the basis of the differences in gas. And helium is another interesting gas that makes balloons go. Like, most of you don't even know that the balloons that go high are not the balloons you fill with air. You know, when you blow balloons with your breath, it actually stays on the ground to look at you. So So the balloons that fill with helium are the ones that go very high and high because of density. And if you inhale or take in helium gas, it literally affects the pitch of your voice and takes it higher. Even if you have a low voice, it will take it high enough. So interestingly, that's what helium does, a whole lot of interest. And all of those things are gases, by the way. And then you have radon. Radon too is one. This one is a radioactive gas, and it's inert as well, and it's toxic. So this is a radon gas test kit, because you don't want to have radon in your house, and the sources of radon are basically from the soil. I think the soil and rock, those are the sources of radon. And I think all the companies come up with test kits so that you put them in your house for a period of time, and then you send it back to the companies, and then the companies will do a check on this device and then tell you whether or not your house, because the radon is radioactive and it causes lung issues, like lungs, your breathing. So some people have issues with breathing on the basis of radon poisoning, because they have inhaled radon gas, and if these people happen to smoke, it makes it even worse. So they have breathing issues and a whole lot of complications that will cause death in the long run if not properly taken care of. So that's why people are very much keen on ensuring that their houses don't have radon, because you can be inhaling radon in your house and not even know it, because it's generated from soil. So I think that's it for this lecture for the second part. So we'll continue with the third and the fourth part, and hopefully this week we should have all of the videos out, and by next week we'll start a new lecture. So thank you so much for your time, and please take notes when you watch the videos. Take notes. If you have questions, forward a message, and I will get us I will fix us. I will actually send you the times for the online office hours, and then you can ask your questions. So those of us that have face-to-face, you have the opportunity to come to the class, and we have a fun time talking, and you ask questions, I give you answers to questions, because I'm not scared of your questions. So that's it for this lecture. See you guys on the part 3 and the final part 4 as well. Thank you, and bye for now.